All right, so today we're going to take a filter review of the Helio Spring flight control board. Okay, so what we're doing to give this thing a good vetting is I have a everyday man's quad here. This is a Martian 2 frame, which is a clone of the Alien frame style. Actually, pound for pound, it's a inexpensive frame, but the noise performance, the resonance of this frame is great. It doesn't have weird noise characteristics. Actually much better than the Chameleon or the Rooster. Those aren't that great, especially for a premium frame. It kind of stinks a little bit, but this one, the frame's not an issue. Props on here are the HQ 5050. Some of the tests on the data download that you'll see here in a second were the T-Motor 5143. Yes, I got that right. And both performed really well in the noise testing done by Mark Bismar and Dom Lee. Thank you guys again for that. So it's not like we're using extra noisy props. And these RCX motors, you can go back to my noise testing, are the same motors I used in that, and you can see how with a proper prop they perform great as well. So we don't have particularly noisy equipment. We have a half decent solder, the solder joint heard around the world there. So I don't claim to be the best builder, the best solderer, but this build quality, both boards are subject to the same quality, so that's kind of a non-issue. What we have here is the Helio board on the bottom, and then we have a CL Racing F7 board on top, both in the stack, PDB down below. We have capacitors on each CSC. They're kind of tucked in here and wires brought around to tie in. And the video, there's basically no video noise, and I have the I have the camera running right to the VTX straight for the signal, and then power for the camera and the VTX are coming right off this PDB, which has no electronics in it, and there's no lines or no noise. So that's telling me these capacitors are doing a great job. Honestly, I'm really kind of impressed by that. I think I have less noise now than I did when I had a Maytech board on the bottom, but maybe not sure. But yeah, so that's not an issue. Also, we don't have to worry about EMF because we have each ESC out here, so we don't have to worry about electromagnetic interference. And I'm going to show here in a second how the top board always gets a slightly bit more noise, so we're giving the Helio a little bit of an advantage here, right? Because he's the bottom board. Essentially the ESC wires are going to the signal wires are going to the Helio. Everything's wired to the Helio. The Helio's flying the thing. The slave board, the CL Racing F7 board, is the only thing it has VBAT power, so it gets power, and then the receiver is wired into the Helio board, but then there's a wire coming off of the receiver as well, just for signal, that also goes to the slave board. So when one board, they both arm at the same time. When I switch flight modes, they both switch flight modes at the same time. They both disarm at the same time. This thing thinks it's running it. The only difference is the signal doesn't actually go to the ESCs. That also does make a difference in the PIDs. You can't we're not going to be putting a lot of emphasis of anything downstream than the filtering, because the calculations are doing some things in this flight controller. So the logs on this flight controller, if you're looking through them, and the PIDs are expecting the thing to react, and it does, but it's based on the reaction of what this is commanding, not what this is commanding. Generally, you can see they line up, but over a long period of time, you can see I terms start to accumulate because the quad's not actually addressing what it thinks it needs to do with I term, that kind of stuff. So you can't really pay attention to the PIDs. Motor traces, not really. We're going to really be focusing on the raw gyro data, which this is collecting because it's just stock Betaflight. This one we cannot collect raw gyro data, and this one is also applying Betaflight filters, where the Helio is applying its filters. So we're going to compare the gyro signal that's coming from the Helio board to what Betaflight would produce stock. Basically with the stock filters, no magical quaternion stuff, just plain old filters there, and see what that gyro signal looks like for both. And then anything downstream of that, the PID stuff, we're not going to be really looking at the PID so much. I did have them set the same, so you can kind of look at it a little bit, but you got to, you know, I wouldn't put a ton of emphasis on that just because of that. This thing doesn't actually get the opportunity to command the quadcopter to do anything. Okay, so now we're connected in. Looking at this, we have the Helio connected. We're using Betaflight for the firmware. The configuration we have, and we have Betaflight on both the Helio board and on the slave board as well. We're running 32K mode on the gyro, so the gyro is sampling at 32K regardless, because that's how that works. And then we are downsampling to 16K for what Betaflight is reading from the gyro hardware, and then just using the PID loop with the same thing. Just remember, when you're at 32K, you're sampling at 32K regardless. Same thing when you're in 8K mode, you're sampling at 8K. Even if you have this set to 4K, it's still sampling at 8K, the hardware is. So you can just scroll through the settings here real quick, and I'll show you why. I'm going to just breeze over this because I have a file you can look at. Here are the PIDs, stock PIDs, and then the filter setup on the Helio is the defaults that it has, which basically for the gyro, all the filtering is turned off because Helio's magic thing is, you know, doing its magical magic. And D-term filtering, you know, it's stock, but we're not going to really be going that far down the tracks and looking at the D-term itself. Everything else is pretty close to stock. I did use RC interpolation and turned that off because I wanted to have abrupt changes in the RC signal, basically the radio controlled signal. I don't want it to be smooth at all, and I could use those to line stuff up in the black box logs, which is a neat little trick. For black box logging, we are logging at 8K, so we're filling up the card pretty quick at 16 meg. The slave board had 128 meg of flash, which is awesome, and really love that about it. The only thing that you do, if you do have that board, one thing you do need to know is you have to use their hex until this one pull request gets merged, so you don't hurt that flash, because it's I guess the size, Betaflight doesn't currently recognize that kind of chip yet, or it works with it but it could hurt it. I don't know. Bruce Lovelock was telling me about it, which is eTracer. The other thing that if you do use it, even with their hex, is don't use the save to flash file here to download your logs. Use this. This takes a really long time for some reason for the CL Race and AF7, but if you use this, it you know, it just copies the stuff over like normal. Which also great about that other board is when you hit erase flash, it happens just like that. It just erases it right off the bat. Where like on the Helio here or any other board, I think it takes like 15-20 seconds for it to erase, which I've done a lot of logs, so it gets annoying after a while. For more details and all kinds of data, if you go to tiny.cc/filtercalc, and if you go into this Helio Dynamic Notch Hex folder, first you can get a copy of a Helio hex or a build that the Dynamic Notch actually works in, and you can utilize it if you want. Now in this test I have it turned off because it's not the recommendation, all that kind of jazz, but that is there. The other thing you can look is there's a dump comparison that I did between the two flashes to the boards. But you can see there's IMUF stuff in the Helio one that's not in the other, and you can see my IMUF settings right here. I did notice some interesting things like this PID level, set PID level equal 50, 75. That's a Helio thing. I don't wonder what that is. But whatever that was stock, that's what I left it. And yeah, you can see the rest, and you can see this is the actual dumps from each and a comparison of them line by line, so you can check that out to your heart's content. Here, I'll go and save that. Also in here is all the testing that I've done. So this is the first Helio log bench test I did the night Helio. This is all the folks, I'm sorry, this is from back in the day, which kind of got me into this when people were asking for some help on their Helios and having some trouble. I was trying to help out, and the rest is history. This is the bench test I did when I published on the Facebook page. Did a quick full flight and then another full flight down here. Did a bunch of testing here to get filter equivalency, which we'll talk about here in just a second. Okay, so the first full flight test I did, I actually had Betaflight installed on the Helio board, so that's this folder right here. And looking at, this was Helio stock Betaflight, and then this was Betaflight stock 3.5. You can see the differential. So this is the Helio filtering. This is the Betaflight filtering. Now this debug mode, this is not raw noise. In the Helio builds, in the Betaflight builds for Helio, you can run, there's a debug mode called IMUF, and you can run that. I don't know what the stuff is, but I thought, well, might as well see what it produces. So looking at these two graphs, what we're looking at here is throttle range. So this is at 0% throttle, 100% throttle, and this is the noise frequency on the left. So you can actually see your motor band right here. And if somebody was just flying stock Betaflight, first thing I would say to them is, you don't have the dynamic notch turned on. This is basically just looks like a stock filtering without the dynamic notch, and that's the dynamic notch kills this motor band. As you go up in throttle and this peak motor noise, these vibrations move up in hertz, the dynamic notch tracks that, and it's actually working on this axis really. So if you're used to seeing a black box log spectrum analysis, you can see the hertz and the amplitude of the noise shows on the y-axis here. This is the higher the amplitude there, and then the frequency of that noise is across the bottom. When you're looking at a plasma tree log of this, now the frequency is across the side. Amplitude is basically shown by a darker yellow. So if you see a dark, that's the waterfall part of it. You see a darker yellow, it means it's a higher frequency. And then they have the throttle percentage. So this is cumulative. When you're looking at black box spectrum analysis, this is across the entire flight. So this noise could have happened only at one spot in the flight, and it's going to show here. But that might just have happened like right here. So it matters. Like you can't, for when you're literally looking at this, you have to have a clean log. You can't like be hitting a tree or things of that nature. Whereas this, with a plasma tree log, it's not cumulative. It's showing you at what throttle percentage and the frequency it's at, and then all the amplitude is also just in the yellow. So comparing these two, you can see we have a motor band here that's not being attenuated well, where it is in Betaflight with the dynamic notch, and then the low pass filters are getting basically the orange data in the background. Now you will notice down here this yaw axis. Through all the testing, I feel like the yaw axis is not performing well. I don't, 32K gets a little problematic. I mean, it has an IMC gyro just like everything else. It seems like the yaw axis on the SP racing board that I have is fine at 8K, but at 32K the yaw axis is awful noisy. So I don't know what that would be other than just it's a mechanical thing with that the specific gyro that's in there. These gyros are made by NVenSense, which is a separate manufacturer, and maybe just that specific one, or there could be some other reason. But it does seem like the yaw is a little noisier, but you can see pitch and roll. So we're going to focus a lot on pitch and roll. I'm going to go with that the yaw is an outlier. You could go the other way and be like, all right, Helio, there's a lot of Helio fans that are going to say, oh, no, it's because of Helio. All right, then fine, it's handling yaw better. So, but the other two, it's not. Now, as a part of this, somebody could say, well, that's great, but you're over-filtering it. What's your latency? Because that's the other part of that, and they're very right. Latency is a big factor. You can throw on a ton of filtering and make these graphs look all nice and blue. However, if the latency is horrible, well, then that's problematic. You're not going to handle prop wash well, flight characteristics aren't going to be good, and so on and so forth. So what we really need to do is we need to get to compare latency. We really need to get the beta, this is the route I went at least, really need to get the Betaflight filtering equivalent to what the Helio filtering is producing noise attenuation wise. Then you'd have apples per apples on attenuation strength, and then you can look at phase delay on the gyro signal and see where that lays. Okay, so for what I did there is basically did a lot of hover testing and punches and rolls and stuff, just basically some line of sight. I kept going back and forth, playing around with the filtering on the slave board, which is the CO Racing F7 board again, and played around with a bunch of different filter settings, like I said, and kept Helio basically the same and trying to get filter equivalency. So here's what I came up with. In Betaflight, if you have a gyro filtering of a PT1 filter at 100 Hertz and a biquad filter at 750 Hertz, this is the noise attenuation you get from that. This is the Helio of the same flight. So you can see, they're not exactly the same, but they're pretty darn close, and Betaflight's filtering a little bit better in this scenario. So maybe this could be higher. So maybe this is really 150. So here's 150. You know, this is 150 for the PT1 and 750 biquad. So you see, oh, that's a little bit worse. Now, we have to keep in mind, just like the data I showed before, that the slave board, the secondary board, is always showing a little bit more noise than the master board, than the lower board, the primary board. Okay, so I need to interject this little fact at this point. So another gentleman, Binding, did a bunch of tests with this same setup where he had two boards, two flight controllers, the exact same flight controllers, thank you Airbot, for in the same quad, in the same stack. And we were looking at phase delay of soft mounts, which I never published a video yet on, and it's been like 9 months, and I apologize, but syncing logs, we have to talk, Binding, it's not that simple. Anyways, you can see on here that the main board, the bottom board, had a little bit less, and it's the exact same board, exact same firmware, exact same everything, had a little bit less, so we're only looking at raw noise, had a little bit less raw noise than the secondary, the higher board, and which was difficult when we're trying to look at soft mounts because the top boards were soft mounted, the bottom board was not. And I kept seeing the top boards had a little bit more noise than the bottom. I'm like, how can that make sense? And so I said, well, can you flip the flight control boards? So now he flipped them, and we realized then that the secondary board, again, just always had a little bit more noise than the primary. So in the testing we did here for the Helio, it has an advantage, right? It's on the bottom. The secondary board, the slave board, is on the top. So we're giving Helio advantage. I specifically wanted to do that just to make sure, you know, my results are good. So this 150, that may be it. It looks like there's more noise here, but it is the secondary board. So there's a between, you know, that low pass filter being a PT1 between 100 and 150 hertz seems to be, you know, 100 is a little bit more attenuation than what the Helio is producing. 150 is a little bit less attenuation than what the Helio is producing. So somewhere in between there. And there is a little bit of margin error because that primary and secondary. Here's the takeaway. Make sure your flight control board is mounted to lowest to the deck as possible. Obviously, if you have a 4-in-1 ESC, you can't really do that. Well, actually, you could. I see a lot of people, or I saw somebody talking about mounting your flight control on the back of the quad. I think that's a horrible idea because it's not the center of where everything spins. But you could mount the 4-in-1 ESC to the back of the quad and then then you don't have to worry about EMF stuff either, and get your flight control mounted to the base as close as you can. So the next thing is phase delay. We got to compare phase delay. Now we have the filtering attenuation equivalence, right? So phase delay. What the heck is phase delay? What is it? Phase delay. Phase delay is essentially a product of the math that you're doing. It has nothing to do how fast you're doing the math. Doesn't matter if it's 32K or 1K. It has nothing to do with the speed of the calculations. It has to do with just the math that goes in. It's like if you take 5 numbers and you average them all together, the average is not going to be each individual number. It's going to be the average of them. So it's the same thing. It's not an average. It's more complicated than that. But you can see in this graph, this is the raw noise. This is what the gyro is picking up, unfiltered, completely unfiltered. And you can see it's pretty smooth here because the throttle's 0% in this hard roll. But then the filtered signal is here, and you can see there's a differential. Why is this down here? It really should be up here. Well, that's what the phase delay is. It's because of the math. Unfortunately, when you apply filtering at 100, 200, 300, 400, and up hertz, you have your cutoffs way up high, it still has a phase delay really far down low. And if you want to explore that in all kinds of detail, you can open up my filter calc tool here, and you can set your filters and look at the phase delay at the low frequencies. This is our control frequencies. This is our prop wash frequencies. Even when you have filtering way up high, look, you have 1.1 milliseconds of phase delay all the way down at the bottom. And that's honestly what got me into this, because there used to not be a lot of information about that out there. So you can see right here, that's about 2 milliseconds. And do M for mark point. You can move over and you can see that's about 2 milliseconds. What you really need to do is turn off expo. So you can see expo here. And then you also need to basically try to make a point here and then take your eye and go straight across to here. That's going to be your phase delay. You can see what 2 milliseconds of phase delay essentially looks like. 2 milliseconds is going to be 500 hertz exactly. So we're not exactly at 2 milliseconds here. And you can use the Alt key and move that around. So that's actually 503. That's actually 2 milliseconds right on the dot. So you can see what 2 milliseconds phase delay looks like. It's really close when this is at 100 scale. So it's hard to see. Generally, when we're talking filtering in Betaflight or whatever, you usually have about 2 milliseconds on the gyro signal itself, and then you have another 2 milliseconds generally on the D term, so a total of around 4. Usually gets up to around 4 or 5. If you can keep it in the low 4s, that's pretty good, but you have to have a low bass noise for that too, or fairly low, or really great filtering. So Betaflight 4.0 has some dynamic filtering going on that can really help along with that, but we're not going to get into that subject. But just keep in mind, it's 2 milliseconds, anything below, like around 2 milliseconds and below for a gyro signal, that that's pretty good. Anything above that, it's not so great. And so that's where we're really focused here right now, is the gyro, not the D term. Okay, so let's look at some of the comparison logs. So what I did is, with these filter setups, I have the Helio board, and then I did a trace for the SP Racing F7. Basically both logs, same roll, just did a line of sight roll. As you can see the phase delay in those other 8K logs I had there, just from other testing and whatnot. So we don't need to have a full flight just to get a baseline going here. We will get to a full flight, but initial setup here to try to get filter equivalency, you don't need to. So you can see 150, 750. Now the other issue that we run into with logging is that syncing up logs is not that simple. I don't fully understand why, but the best way I've combated it is to essentially use that RC interpolation of 0, so you can see these abrupt steps in the RC command in both, and then you can use those to line up the images. And I basically just did a screenshot and then took out the white space on this one so you can kind of see through the two. So you can see that here. And if you look in, we're really lined up. They're basically lined up on top of each other. They're slight differences between the two, but there is another factor here that we have to recognize, is that the top gyro and the bottom gyro, they're not exactly at the same position. So their rotational rates can be slightly different. And that I believe is what really leads to this. If I look down through the details here, you can see in this image here the full rotational rate of the purple gyro, which is the slave one at the top, doesn't get to the full rotational rate of the Helio, and that has nothing to do with filtering here now. This is not a phase delay. When it's horizontal across the screen, that phase delay is not a part of it. And if you look in those logs specifically, you will see that just at the peak of the rotation, where it's just doing the clean rotation through the roll, you can just look at the numbers yourself. I mean, that's a lot of the point of this presentation, is that all this data is here for you to look at yourself. It's not me, it's just the data I'm seeing. I'm just relaying what my observations are. And here was the lineup on the 100 and 750 here. And if I zoom down in here, you will see that the red does appear to peek out in front of the other one by a little bit, so a little bit less phase delay. Now here on the back side, when I line those lines up, it doesn't, I would say like right there, they're right on top of each other. So that, there's a little bit. I think 100 is a little. I think that lower filter could go up a little bit, like we talked about before, more like the 150. And if you're used to looking at this stuff in black box spectrograph analysis, so this is the Helio, and then the Helio Flight 7 for the hover and just punching test, and this is the 100 and 750 for the slave board, and you can see just the noise profiles. Now, what I found this was interesting is the Helio board, the noise was lower all the time. So you can see the peak motor noise was 275. With the Slave, it was more like 405. So I don't know why that is. Obviously, the Helio is doing all its filtering the IMUF, and then it's passing it to Betaflight. I don't know why that would be the case. You can see the raw noise in the. So this is the raw noise from the CL Racing F7 board, because I can record it because it's just stock Betaflight. And you can look at all that noise way up here. Now we're sampling up at 8K. We're only able to do the spectrums down to half that rate. But you can see the noise is up here higher for your motor noise and whatnot. It's definitely, you know, above the, so it's like 403 right here, and then if we do our gyro, you can see that 403. So I'm pretty sure this is correct, the CL Racing F7, because it's lining up with the raw noise and all that jazz. I'm not sure why the Helio is lower. And lower is not better, lower is worse, and that could just be, I don't know what that is. So ultimately, the noise profiles, though, the amount of noise being attenuated in both, look about the same. Okay, so that's all good and fun, but those were just hover punch tests. We need a full flight of this. So I went out, did a bunch of 180 turns and some split S's and power. I think I only did one power loop, but this is what I got. It's like 18 degrees outside, so I was in and out. On the left is the Helio attenuation. On the right is the Betaflight stock or CL Racing F7. So you can see the CL Racing, the filter setup there did a little better. Again, we had that a little bit more aggressive. So I did do a test on this board with an 8K, and you can see now the yaw axis is fine in 8K. So if you're having yaw issues and you're running 32K, then just run 8K. Maybe that will fix it up for you. Logs for the full flight, again, are at the link you can download. It's just right down here, full flight. Here's the two logs, and there's a plasma tree up above it. What I did do then as well is I made a little GIF comparison. So this little GIF goes through the Helio and certain spots on, wait till this gets down to the beginning. So this GIF will cycle through a bunch of spots in the logs and compare them both. So here's prop wash condition on the two. Here's the same roll on the two. They look really dissimilar to me. And here's the same thing at full throttle. So just, you're really trying to look at the fully filtered traces, and this is the actual gyro signal. The prop wash, I look at pit error, just because it equalizes stuff a little bit, but it's the same thing. So you can see just the traces. There's slight difference in the traces, but what I'm really looking for is there more phase delay in one, and I'm not, and this is the, you know, again, the 100, the PT1 at 100, and I'm not really seeing, especially in prop wash, I'm not seeing them shift to the right or anything. I'm seeing that horizontally they're staying at the same spot. Vertically, they're different from each other. And that could have to do with the vertical offset and the stack of the boards, but horizontally they're about the same. So I guess my takeaway from this, and you guys can draw your own conclusions by the data you can see there, is just my conclusion is that the filtering from the Helio processor is essentially equivalent. I'm not going to say it's the same, but it's producing the same result, it appears to me, to be just a PT1 filter at 100 hertz and then a biquad filter at 750 to hit those high frequency noises that we saw on those traces at 32K mode. So I did record some quote HD of the full flight. That you can check that out. Hopefully it helps. It's always nice to see a little reel of footage, I guess. Thanks everybody. Hope this helped.